Have you ever been asked what sort of latency you can expect in an IoT solution from the edge to the cloud and back? Or maybe what sort of latency you should expect from a REST API if you're calling an application server from the other side of the globe? I'm Greg Eva. I have been asked those questions, and today we're going to look into some testing that I did recently, specifically on those two questions and what the implication of latency looks like when we're dealing with Kepware to ThingWorx communication and ThingWorx REST API calls measured from different data centers around the world. So first, let's start with Kepware. My approach has been to send a message from Kepware and get some things connected in ThingWorx and really send telemetry messages up from Kepware to ThingWorx, and that message is received at ThingWorx. Key here is that the timestamp of the original trigger is maintained. So this ping trigger, you can see here, it's alternating. This is a 10-second loop, so it's alternating for about 6 of those seconds. It's staying at 1, then it's going to 0 for 3 of those seconds. So every 10 seconds we're going to have a low to high transition, and considering the send to ThingWorx is going to be configured to send on value change, when we change from the value from a 0 to a 1 or a 1 to a 0, we're going to get the timestamp at the edge here on Kepware, which is going to be stored. If we come and look in the actual values here, you can see that the ping trigger going to 1 or 0 has a timestamp that's changing. The timestamp is actually changing more frequently here in Kepware because the value is actually changing based on this simulation user function. But considering that it's only being sent to ThingWorx based on the configuration of send on change, we're actually only seeing 2 of those changes on the ThingWorx side, which I'm then catching in ThingWorx. If we come into here and we look at the property configuration, we can see I've got a number of properties. Here's this ping trigger that is bound to that remote tag in Kepware that we're looking at. And we can see that it should be triggering kind of back and forth, essentially once every 10 seconds. There it goes. There it goes, the retrigger. And from there, I'm firing off a subscription. Ping received. And this subscription is just looking at which transition did I just make. 0 to 1 transition being the becoming true. I'm going to essentially take a value. I'm going to set the Pong response into this other tag. So I'm using a secondary tag to send a value back down. And I'm going to reset the calculation completed Boolean. And if it's the other one, this is actually on the return. So this is that 7th second when we go from 1 to 0. At that point, I'm going to actually do the calculation because I determined that I've received the Pong response value. If we come back to Kepware for a moment, in Kepware, we see this Pong received. This is that other secondary tag in ThingWorx that we're essentially popping that 1 back onto this tag that appears in Kepware. And basically, it's not going to arrive with a timestamp. So the moment that it arrives in Kepware, Kepware is going to timestamp it, and that's going to trigger a value change. And so the new value is going to be sent up to ThingWorx, and we're going to get it back with the timestamp that's filled in. So we do get that received. And then when I come back to the code here in ThingWorx, all I'm doing is just doing a subtraction, of the 2 times. You can see it's a little bit more complex than that. Here I'm doing get property time because I want to take the property time off of that ping trigger. Sorry, this one. Pong response. This is the one that's going to be filled in the second step. And event data, old value, time. This is the old timestamp, so the triggering timestamp, not the one that's going from 1 to 0, but it is the previous value, so the 0 to 1 timestamp on the ping trigger. Just some filtering in there, and I put the timestamp here that we calculate this on, and this is going back, the calculation completed 1, and the timestamp is meant for the control system, because a big part of this process is really, let's call it a proof of concept of ensuring that such an open loop telemetry flow is established and can be maintained with the control system. So here we can see back on the Kepware side, I could pass these values back into a control system, whether it be a SCADA or a PLC or something, where the intention is, if I'm relying on such communications flow, that I'm going a little bit further than just doing a heartbeat up to ThingWorx. I'm actually bringing the communications back, and I'm saying that the calculations that I'm expecting to happen, like a scoring of a model or something, are actually happening on ThingWorx. I know when the last time that happened on ThingWorx, and I can take that timestamp here, the calculation timestamp, and I can do a diff between an actual time. I'd have to do this in a SCADA or a PLC here, can't do it in Kepware. But the intention is really to come up with a mechanism by which the control system can understand when the last time it had some form of cloud-based calculation that was done, so that we can ensure the latency is not only operating in a reasonable fashion to support an open loop type control, but also so we've got a heartbeat coming back down from the cloud to the control layer. So from there, that value that we saw, I was just posting this into this telemetry ping round trip time, and you can see here this is coming in at about 218 milliseconds. There is a little bit more to this example that we're going to look at if we come back over here. I'm also leveraging the ping channel. So this ping channel is from my Kepware. It's pinging the ThingWorx server. And I really wanted to look at not only the response time for this whole telemetry round trip, but also just what the network latency is, so we can compare the two to try and eliminate certain factors like understanding network latency issues and how those are impacting this open loop control channel that we're establishing here. Right, so I mean, you saw it in Kepware there. Having a quick look at it here, I mean, it's a bit of a process that I built. You see the calculation is triggering. You see this timestamp is changing, and really what our target here from my testing is this calculation. This stuff is more proof of concept, but there's a couple of things I think that's worth pointing out here. Is in order for this to work and get us a real measurement, as far as a real measurement as what the minimum might be, I have to make this go as fast as possible, because otherwise the default configuration is 1 second, right? So when we have the property configuration over here on the scan rate is by default 1 second, and it's telling Kepware, hey Kepware, I would like you to check this value, ping trigger, every 1 second. And if you see a change, push it up, right? That's what we saw right here. Push based on value changed, scan rate. You see I've got 10 milliseconds. The reason I have 10 milliseconds is I am very certain that this value is not going to change very quickly, right? It's not an analog value, it's a Boolean value. It's only going to change 2 times every 10 seconds. So what I'm doing is I'm scanning the Kepware cache very fast on the ThingWorx client side, so that the ThingWorx client built into Kepware is going to see this transition as quickly as possible. Now it's a 10 millisecond scan, so we do have a slight amount of time there. It is being pulled. It's not event driven, but this is going to allow me to detect this ping trigger change as quick as possible, so that I can send it up. Because of the fact that we are timestamping it, based on its change. If we don't catch that quickly, we're going to be doing a false calculation by artificially adding delay into the overall communications. And it's the same on the Pong received. I've done that so that I have a 10 millisecond scan on Pong received, so that once it gets there, we quickly get it back with that timestamp so we can do the calculations. So this, there's one more thing I did in order to make this go as fast as possible and to support the test, is if we come into Kepware and we look at the ThingWorx native client interface configuration, you can see what? This right here. Publish floor, 0 milliseconds. This is not normally 0 milliseconds. It's normally 1 second. And it says here set to 0 to send updates as fast as possible. I have it set to 0. That means I want to send them quickly. There's downsides to this, right? And this is that I can overwhelm my ThingWorx very easily, because if I have many Kepwares that are connected, or if I have a lot of different tags that are all communicating, basically on any change that's detected, it's going to send that through to ThingWorx. So this is normally used as a buffer. By default, it's 1 second. It can be larger, but this is used as a buffer to catch all the changes that are happening within the client inside of Kepware, so that data is batched between Kepware and ThingWorx, and so it doesn't come in all these tiny slices, which, you know, multiplied by 10, 20, 30, 100 machines would become an issue very quickly. So I've set this to 0 for testing purposes, but it's highly unlikely that you can do that in a production environment. So coming back to our test here, this is being collected. You might notice that they're being logged over here. I've got 2 values that are being logged, and those are just popping them into a value stream so that I can have a look at them. I don't really know anything about building mashups, so I don't have a mashup. I'm using InfluxDB to capture the values, and then we can have a quick look at those values over here. I'm just using chronograph here, and if we just query the InfluxDB, I've got some of those devices, that one we were just looking at. No, it's not that one. This one. So this is the device that we were just looking at. And if I look at this network ping, I have to change this around a little bit. Line, there we go. Past 24 hours. And so here you can see the just all those value changes coming up from the ping. This is another mapped property over to that ping channel on Kepware. And you can see those latencies that have been recorded. So I've built this out. This is the same if we turn that off and we have a look at this one here. You know, I've built this out into a series of dashboards, and the dashboard just enables me to have a look kind of more broadly at all this. And so here you can see network latency and that open loop control telemetry latency that are plotted on 2 charts on the dashboard here. And what we were just looking at was just a VM running in Azure here in Western Europe. And next step to all this, not only to see how quickly these types of communications could go, kind of to get that open loop control mechanism for doing some cloud calculation, but was really also to look at this across the globe. So I deployed a number of virtual machines in various parts of the world. You can see them listed here: Ireland and AWS, Japan AWS, Singapore, Virginia AWS, I think I said Japan already, Netherlands in Azure. So the ThingWorx here is running in Azure in the Netherlands. So the one that we were actually just looking at was this particular one, Netherlands in Azure. And this, you know, although it's got certain limitations, it is meant to give me a representation of some of the different impacts of latency when we start to look at different geographies and distance between the server, as well as going from different cloud providers to also just kind of standard on-premise deployments. So this one here, France Orange ESXi, this is an on-premise deployment here in my office, where I have a professional VDSL2 connection. That's pretty good, but it is also not, not a tier 1, tier 2 connection between cloud to cloud providers. And so if we just start to have a look, maybe before we start to analyze the data a little bit, I'll tell you about this third one here. I couldn't really leave this alone because, this is representative for sure of Kepware to ThingWorx traffic. But ThingWorx also relies heavily on REST API calls, whether they be for interactions or whether they be for mashups UI and whatnot. So I wanted to have a look at what the overall round trip time and latency impacts look like when we're talking about API calls. And so this is what this is down here. If we come back over to the Kepware machine for a moment here, you can see here I've got Apache JMeter that is set up and running in a loop, and basically I have a thread group, a single thread that's running using some different user-defined variables. Previous latency is the value that I'm capturing from the last test. Target entity, target property. This is where I'm going to publish to, and that's the entity that we were just looking at that's logging those values into the value stream on Influx. And target property is the name of the property where I'm going to post that to. And then this loop controller is just an infinite loop that I'm calling this particular update property values. And you can see the JSON payload here where I'm just subbing in, putting the values in there. I'm not putting a timestamp because I'm allowing the ThingWorx to provide the timestamp. I don't really know how to do that in JMeter. Ideally, it would have been better if I used a JMeter timestamp because then all the timestamps would be from the edge. And here this is clearly a server timestamp, but it's not really a big deal. I want to see the trend mostly. And I will also just point out here that I have Keep Alive turned off. So each time we're doing this execution, we are establishing a new connection. So let me just stop that for a moment and then enable this. I've got the results tree and tables disabled because of the fact they use more resources. And turn the graph on as well. I don't really need the graph. And let's relaunch this. So this you'll be able to see here in a minute that it's just running. I've got this timer delay that's putting a 10-second delay between each of the executions, and then it's just re-executing that update property values that's posting the last test response time or latency. And so you can see here update property values. I guess it's posting the sample time. It's latency. It's posting this value here, latency, into that property, which is then the data that's being posted back to ThingWorx after. So I did it this way. I mean, I could have done something more complex, but I did it this way. I wanted to keep everything in the same approach. Everything's coming back into the entity, and just using standard ThingWorx mechanisms to capture, treat, and log the data. And then this is running in a loop to feed us back our service executions. And so you can see down here that this is the REST API results that are coming back from these various 6 instances scattered a little bit around the world. All right. That's a bit long, but that's the setup. That's the test. That's how I've built it. And I think it's relatively representative of a number of aspects of latency, and it does starts to give us a good picture of things. This is the past 24 hours, but let's kind of zoom into a particular spot here where we can start to kind of compare a little bit. And I'm going to start with Netherlands Azure. And this one is interesting because you can see it's pretty much between 0 milliseconds and 2 milliseconds. And the reason for this is it's in the same data center or building as the ThingWorx server. So this is a good benchmark to tell us what we're talking about here when we're talking about removing any network latency, right? Running in the same building. So this is essentially just application type latency. So all of the things as far as establishing the connection, sending it up through the OS, sending it to and through Tomcat, getting to ThingWorx, receiving the message, translating it, doing the property update, putting a new property back, sending it back, all of those steps. This is really what we're seeing here with this couple hundred milliseconds. So this is really good baseline to give us kind of a picture of what that looks like without any network interference. And, maybe next we'll look at France, this one here. Here we have a pretty good network connection, very good network connection, I will say. You can see it's quite reliable. We got a little bit of jitter on the ping latency here, but reliably at around 30 milliseconds. And we also see that the telemetry response is about what we saw previously with this 30 odd milliseconds added. So this is really kind of what I would have expected to see, and maybe I'll say that it's something that's reasonable to a plant, an on-premise implementation. What I will say about this, though, is that I did have some issues with the ESX server, just the Windows configuration, actually. So we do see some spots around here where it slightly goes up. And over the past days, I have seen some uncertainties there. They really seem more to do with the virtual machine that's running on here rather than anything to do with the network. So next, let's have a look at Ireland. Ireland is, there's a channel between the two, and clearly here what we're seeing, that's no good. Let's get rid of that big spike. Here what we're seeing is very reliable, 17, 18 milliseconds, which is far better than obviously my 30 here. Pretty far away, but I think what we can deduce from this is we've got very good cloud-to-cloud interconnections here, tier 1 or tier 2. So it's providing us a very reliable network connectivity and latency, and we clearly see that in the network latency figures, right? So network latency is really the indicator, I think, that many people should be looking at and watching to understand not only reliability, the network type latency, but also if there's any variance over time. And we'll see some variance on the Japan side. And then here for the execution, similar to my ESX server, but you can see it's a little bit more reliable. I will point out that this is between Azure and AWS, so this is still very multi-cloud, kind of cloud-to-cloud. This is very good results. And when we go over to the US, chronograph is a little bit annoying here with this. There we go. When we go over to the US, very similar results. So I would say once again, good cloud-to-cloud transatlantic hookup going on here. Obviously, it's quite far, so we're going to pick up some reasonable amount of latency. But this was really the question specifically around distance, is when we start to go very far from the server, how does the application start to perform, and what sorts of impacts might we see as far as round-trip response times for things like this open loop control mechanism or even REST API. So we see we're still really, really good, like 338-ish. And we haven't really been looking at the bottom one here, but Virginia, REST API is much better, right? Because of the fact this telemetry ping, it's got a fair amount of overhead to everything that we're processing there. And here we're really hitting the REST API, which is designed to be a lot more faster. Let's start to go a little bit further. Let's look at Singapore. Okay. And so Singapore, you can see we picked up a large amount of network latency, which is to be expected. We're also getting larger variance in the telemetry response time. So it's not huge, still quite reasonable. It's quite reliable here, but we are picking up a little bit more variance. And HTTPS REST API calls, super reliable. You can see we're clocking 500 milliseconds here very steadily across the board. And I'm going to zoom back out actually. So let's look at Japan. Okay, so Japan, we'll have a broader look at the ping latency afterwards, but you can see that, we do have a lot more volatility here in Japan, even compared to Singapore. So I was quite surprised. Just see this. Yeah, so this is just the base network latency is 230, right? This is what we were seeing for the telemetry latency on a bunch of the other closer sites. And we're kind of up close to the 1 second telemetry response time, and we are seeing this kind of fluctuation in variance, as well as some peaks that are starting to come out a little bit higher. So this kind of leads me to the belief that definitely got a different reliability of the connection that's going to Japan or to that data center in AWS in Japan. And then this one, this is kind of matching up here with some of this one here. I don't know if this is network related or if it's server related, but in any case, we do see these types of spikes in the Japan region that I was not seeing anywhere else. So obviously I'm not referring specifically to Japan, but I'm using the opportunity to point out that particular hosting region, could be a data center, could be a network interconnection, whatever we have, are going to provide differences that we need to be aware of and expecting. And this is one of the good things about doing such a test, is that it can bring these sort of things to light for us. So that kind of really covers it. If we look back a little bit further, maybe over 7 days, we can still see that here you can kind of see some of these waves across the Japan results, where it's getting faster and slower over different periods of days. So this was one of the other things that I wanted to have a look at this test. It's one thing to look at a test over 1 to 2 hours or 24 hours. But here you can see that we are seeing slight variance, 100 milliseconds, 900 here, 700. So there's between 1 day later, there's 200 milliseconds variance in this overall round trip time. And I guess just to finish, I am thinking about how I can write this up into a little bit of a community post to share some of these things so that others can leverage these types of findings. And really, I was looking for trends in doing this. I was also looking for validation. Some people are looking to deploy multi-site in different geographies and wanted to know what sort of impacts related to latency might come up, as well as what that reliability might look like. And this is where the percentiles are really going to come in. And so I used the same data that's in the InfluxDB there, and I just have brought it into Grafana just to provide a little bit more visualization and dashboarding capabilities than I have in my chronograph dashboard. And I've just made something pretty simple here, where I pick one of those entities, and it's going to draw some graphs for me, similar trend to what I saw before, but it's putting everything on the same one. That's why the yellow ones, the network is so small here, because it's comparative to the other ones, and we have this big spike. So it should be a little bit more visible if I zoom in like this, so that I can kind of go in. And what's interesting here is you notice it's changing the time range, but specifically these ones down here at the bottom, this is to see spikes or peaks. But these ones down here at the bottom, you can see that I'm calculating the percentiles of the 3 different types of latencies that I was looking to calculate. And here you can see 50th percentile, 95th, and 99th. This is going to be, really those outliers, those peaks that might come out one time is going to have a really big impact on the 99th percentile. If there's something that comes out one time, you're not going to see it in the 95th percentile, And the 50th percentile is meaning that essentially half of the results are coming in at this number. So, we can see this distribution. It'd be better if I back out a little bit. We'll see this distribution sort of line up a little bit better over here. And you can see between 200 milliseconds and 240 milliseconds, I have over 400 records. So instead of kind of thinking about this in a trend fashion, I wanted to get into, let's look at the clusters and let's look at the percentiles. And if we come over to, let's say Virginia, you can see, let's go back to 24 hours. You can see the enormous stability here of the ping. Ping response, 82 milliseconds, and 99th percentile and 95th percentile, which is a really good figure that you should be watching, is that these two percentiles. And then here you can see the distribution is quite representative, I would say, probably of just other variants. There are other things going on in ThingWorx, so there is going to be some variance just on how quickly ThingWorx is able to respond and react to these messages that are coming in. And there is a little bit of jiggle in there for that Kepware communications as well. And yeah, and then Japan, if we pop up Japan here, you can see that we do have a little bit more of this variance, but that variance certainly shines through when we look at the 95th percentile versus the 50th percentile. And we see a good distribution that's showing us more along the lines of what those communications look like. So to close, I think I have some slides somewhere around here. Yeah, I do. I forgot to build them out, but with animations. But some considerations to keep in mind here is you shouldn't configure Kepware this way, right? I did this on purpose to try and really stimulate that this goes as fast as possible, just really to support the mechanism by which that I used to test this. You could test it other ways. You would probably blow things up, or you could quickly overwhelm a ThingWorx environment with too many connections like this and too many data points that are flowing. REST API test overhead is mostly on establishing the connection. We didn't really look at that within the JMeter, but because I have Keep Alive turned off, it's reestablishing the connection every time. And this was most of the time, it was around 70% of the overall time was just to establish the connection. And that is a configurable value in Tomcat, the connection timeout, that's defaulting to 60 seconds. So, if you think about a sporadic API call that might happen every once in a while, you're going to have to establish the connection each time. But if you're thinking about other things, like you've got some mashups that are open in a plant, or there's other communications that are already established to the client, then you can maintain that connection, then these results are going to be a lot better, especially when you go farther away. Higher latency is going to mean higher time to establish the connections because there's more back and forths to do so. Results from standard corporate internet access are not going to be as good. As I mentioned, likely we've got some pretty beefy, high-priced direct connections between these cloud-to-cloud environments, tier 1 or tier 2. I'm using this VDSL2 that's about 300 meters from the DSLAM, and from there it flips over to fiber optics, so it's quite a reliable connection, as I mentioned, and I'm going to have less impedance risk on my DSL. So those are types of things that you should think about as far as the entire trip, because things like the cables that are in the ground and things that are happening locally are also going to have an impact on the overall reliability and latency over time. So I guess just as a closing comment, if it's important, test and measure it yourself. This question has come up in the past. I've never measured it, so I'm happy to have done it to get some ideas on what types of speeds that we can be expecting and what type of stability and just kind of latency on some of these aspects. I should mention that I haven't tried to tweak anything other than that Kepware communications. And obviously the situations and environments are going to change based on what application is running, based on where your plant is. And so you should try it out, right? There is one thing that I'm going to check out is accelerated networking. What impact? I don't have accelerated networking here. We haven't really looked at the hardware, but there is this notion of accelerated networking that I can enable over here to really give the networking cards. This is software-based networking here on Azure, giving those capabilities the possibility to process the networking and the traffic as quickly as possible. If these types of things are important for you, this is obviously pretty deep subject and topics, and you need to think about all aspects, including optimizing the entire flow.